Hello, I'm Fourtounis, and I will be presenting how to find callbacks from native code to Java code by scanning binaries for strings. This is joint work with Leonidas Triantafyllou and Yannis Smaragdakis from the University of Athens. Java programs are supposed to be platform independent, and the whole platform is geared towards platform independence. However, many programs in Java still contain native code. In Android especially, a recent survey by Almani et al. Found that 540 out of 600 top free applications in the Google Play Store contain native libraries at an average of 8 libraries per application. This native code is a problem because Java static analysis tools cannot understand it. And in a recent survey by Sui et al., it was found that this is a core threat in call graph analysis. In particular, we find that in Android development, applications may not be successfully optimized or obfuscated if they miss callbacks from native code. This work is about detecting such callbacks from native code to Java code, and the result is fixing unsoundness in the computation of reachable methods in the program. While doing so, we also inform call graph analysis where possible. A key feature of our technique is that it's lightweight. We try to avoid having two big analyses, one running on the Java part of the program and one on the other, and having some way to somehow combine the results. We have a Java analysis, and we start from the strings found in the binaries, and we proceed from there and try to find the callbacks. Native code in Java follows the Java Native Interface specification. The Java Native Interface, or JNI, gives an API that can be used by native code to interact with Java. Here we find an example. We find a function implemented in C, and this function finds a class, hello JNI here, finds a method, hello method is the name, and here is the low-level JVM signature, calls the method, which will give back an integer, and prints that number on screen. We have found that usually strings are used here, and constant strings in particular. These strings exist even in the compiled form of the library. So if we take the compiled library and run a tool to find the strings, we'll find them, and we can classify these strings as either names or signatures. Our key insight is that forming a product of these names times the signatures will give us a superset of the callbacks, and then we only have to filter that set to improve precision and be smart about the actual results used. When we have these callbacks, we can also work further with a JNI specification to determine the missed call graph edges. The first problem that we encounter is just taking the product of all the string names in the binary and all the string signatures is too big. It leads to a very imprecise result, because the superset of actual callbacks is way bigger than what we need, so it gives us too many false positives, because many strings are mistaken for actual method names, like read and write strings may match serializable methods, for example. To fix this problem and improve precision, we don't create one big product for the whole library, but we create one small product for every function. So we look at every function in the binary, and we find the names and the signatures used in that function, and we form a product there. This is done by using Radar2, a very strong reverse engineering tool that gives us back function boundaries and also string references used inside the functions. And there we can know that we have very precise small sets that altogether give us the big picture of the callbacks. Of course, analyzing binaries for function boundaries is something that doesn't always work, and sometimes native code is too hostile to analyze. So here, for some problematic native code, we may not be able to do this filtering. The second problem is callbacks to constructors. When native code calls a constructor, it's to allocate something in the native part of the program. And native allocations, as found by Sui et al. Recently, are a major source of unsoundness. Our problem is that constructors are all named init in bytecode. Only their signatures differ, and this introduces a lot of unsoundness and generates too many false positives. Here, we try to be smart and apply a precision heuristic that says we will accept a constructor only if its class is used in some other way, if a field is written, for example, or if a method is invoked. To reason about fields, we must have a points to analysis, and to reason about invoked methods, we must have a call graph analysis. So, where do we find this analysis, and how do we integrate with them? In practice, we chose DUP, which is a static analysis framework where analyses are written in datalog, and they are written in a way that they work together in a mutually recursive fashion by each analysis, by consuming and generating data from the other analysis. And let me explain more about this, the way that analysis combine together in DUP. So in the left part of the screen, we see two standard analyses, a call graph analysis and a points to analysis. And we have arrows between them pointing in both directions because these two analyses are mutually recursive. Each uncovers more code for the other to work with. On the right hand, we have our filtering for constructors. It's an actual snippet from DUP. You don't have to read it all, just look at the highlighted parts. The yellow part is what we compute as an accepted constructor callback. The blue parts come from the analysis. So, in the upper part, you see that a constructor is supposed to be a callback from native code if some other instance method is reachable. This information comes from the call graph analysis. In the bottom, we see that if a field is used, then a constructor is also considered a callback, and this field information also comes from the points to analysis. But on the last line, we see that we also contribute to the reachability information. We also make the constructor a reachable method, so we inform the call graph analysis. This is a complex pattern of mutual recursion, and having the data log part of DUP do that automatically is really helpful. Now, another problem is that so far we have talked about reachability. We say that we detect a native callback, so we mark the Java method as reachable. That's fine for fixing unsoundness and reachability, but we would also like to fix unsoundness in call graph analysis. What if the native code is behind a native Java method? Shouldn't we form an edge from the original method to the final method, even though it's called via the native code? To do that, we must know how native methods in Java correspond to functions in native libraries, how libraries are linked against Java. And to do that, we have to model JNI Linking to be able to reason about entry points to native code from specific entry points in Java. JNI Linking comes in two flavors, an automatic one and a configurable one. And the automatic one is easy, almost trivial. If you have some package with a class and method, you know what name is to be expected and automatically linked against the Java code. There's an optional signature suffix in case of overloaded methods, but that's it. So if your JNI code respects this convention, you're fine. However, there's also the case of configurable JNI linking. Here, the JNI API gives the developer the capability to link arbitrary function pointers to native Java methods. Look here on the right side, where we see an excerpt from an existing Android application, the Android Terminal Emulator, and we see here a triplet. 3 lines highlighted in yellow. The first line mentions a method name, the second line mentions a method signature, and the third is a function pointer. This triplet will eventually mean that in the Java world, where this method with this signature exists, link that entry point to this function pointer, to this function in the native library. To uncover these triplets is arbitrarily difficult, and for many cases we can uncover them by reading more parts of the binary and reasoning about consecutive parts in the code and trying to find function pointers. This is not always possible because some binaries are hostile and cannot be analyzed or processed by our technique, but it works for a lot of binaries. This handle of linking is shallow. If a native method in Java calls the native library, then the native library does calls inside the native code and eventually calls back another Java method. We don't form an edge from the start Java method to the final Java method. We could if we would process the call graph from Radar 2, but we're trying to be lightweight, so this case will be missed. Here, this is a knob. You can turn it to make our analysis heavier but more precise for call graph analysis. On to evaluation. The first evaluation is XCorpus, where the XCorpus is a suite of Java programs. It gives us a feature report, and the feature report shows all the native methods in these programs. We look at the sources, we find the callbacks, and we verify that all such callbacks are captured by our technique. Our technique detects all callbacks in these benchmarks. These are 3 benchmarks, not 4. The 4th one, log4j, is a benchmark with native code but without native callbacks and serves as a control benchmark. We see here that when there is native code without callbacks, we don't introduce noise. The second part of our evaluation is about Android applications. And here we examine 2 big Android applications, Chrome and Instagram. In both of them, we run them and we examine the native callbacks during these runs, and we verify that we captured them all. Yes, we do capture them all. There's 100% recall metric, and we find all native calls in these applications for these runs. A small detail here is that we go to 100% not from 0, but from some base recall exhibited by the baseline analysis, because sometimes a method may be called from other places in the code. So even though it's missed, the native callback is missed, some other method makes it reachable. And there's also the case that maybe it shouldn't be reachable, but analysis over approximation, static analysis over approximation, makes it so. So this is the base recall metric, in case you wondered. Then we build an application. As I said in the introduction, Android application development has a problem with native callbacks. In Android development, you often have to obfuscate or shrink your application so that it can be distributed via the Play Store. And the two most common program optimizers are ProGuard and R8 with some specific syntax. And these optimizers, they make the developer write a manual script, a script that explicitly contains keep rules, as they are called, rules that say do not touch this method because it is a callback, because it's from reflection, or all sources of problematic corner cases in the language that a tool may not be able to resolve automatically. And each time the developer adds a new native library, they have to update this manual list. Our tool here comes to the rescue and automatically calculates these rules. And as an example here we have Wikipedia, the application, which gets built and repackaged by following a set of 224 rules. And our tool computes 26 rules. Maybe some rules of ours are overlapping with existing ones. The basic thing to get away from this number is that this is a small part compared to what the total number of rules is. And this technique is available in Dup and in the class packager. So we saw that strings and JNI binaries are very good for finding callbacks to Java code. They can uncover missed methods in reachability computation, and we can even fix missing edges in call graph analysis in some cases. Real-world programs can be analyzed and 100% success is shown. Thank you. Thank you for your attention. I'm glad to take questions.